Well, good evening, everybody. Welcome to this lecture. I'm Nigel Mason. I am professor at the University of Kent in the School of Physical Sciences, and I am a space scientist. And what I'm going to talk to you tonight about is a lecture which we kind of do at the beginning to our students on the introduction to courses on space science. And I'm going to take you on a journey. I'm going to take you a journey around our solar system. So we're going to visit all the interesting planets and some of the other things that we have in our solar system and give you a little bit of an idea about what we know, but also what we don't know. So I'm going to say, let's start the mission. Humanity's continuing mission to explore strange new worlds, to search for life, and to boldly go where no one has gone before. That is what we space scientists do, and I wonder if you know where that one comes from. So you all know our solar system. Our solar system is a rather standard solar system now. We now know what other solar systems look like around other stars. And they have planets, and we have lots of planets. We have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and we have little Pluto out the end there. And we'll have a little bit of discussion at the end of whether Pluto is a planet or not. Now, at the center of the whole thing, of course, is the sun. And yes, we do go around it. 99.85% of the mass of the solar system is in the sun. And the sun is made up really of really rather boring chemistry, or boring elements, because 92% of it's atomic hydrogen and 8% of it's helium. But if we didn't have the sun, nothing else in the solar system would work. And it is the source of the solar wind. And the sun does interact with us, not only because it keeps us warm, but it also produces things called space weather. There are particles that come across from the sun and interact with us. And we'll talk a little bit about that later. Now, we have different types of light, and we often talk about visible light. Now, why do we call it visible light? Well, you've probably got the answer to that. The reason we call it visible light is because what our eyes see. And our eyes have adjusted and have evolved to take into account the sunlight. And you can answer the question to yourself, what color are our eyes most sensitive to? And I hope you're all saying yellow, because your eye is most sensitive to yellow. And that is because the sun is that big yellow thing in the sky. So there's automatically a link between life on Earth, ourselves, particularly, and the sun. And the fact that we have adapted, we have evolved to take into account that there is this nice star called the sun in the solar system. Now, we then break up the rest of the planets, which we'll talk about in some detail in a minute, into two types. We'll talk about the inner planets. They're the planets that are closest to the sun. And all of those planets are rocky planets. They're all quite dense, and they all have some kind of metallic core. And often that can lead to a magnetic field. And then we have the outer planets, the ones far out of the solar system. And these are usually large planets like Jupiter, Saturn, Uranus, Neptune. And unlike the rocky planets, they're mainly made up of just gas and liquid. And sometimes they don't even have a solid surface. They might have a small rocky core, a small solid core. But the big thing about these is they all have very large atmospheres. And often they have these planets that have winds and large amounts of storms and everything else. And they're also rotating often very quickly. So we're going to divide the solar system up into these two types, the rocky inner planets and the gaseous outer planets. Now, although in this hour we haven't got time to talk about some of the other things that are in the solar system, but in any solar system course at Kent, we would often talk about some of the other things that are there, not least because it's one of the things that we study in our research at Kent. And some of these things are asteroids. Now, these can often be called minor planets or planetoids. In size, we might be talking about things less than about 1,000 kilometers across, and they live in an asteroid belt between Mars and Jupiter. And every so often, one of them gets knocked out, and we can talk about that again in other lectures. We talk about why they get knocked out, and they crash into Earth. And the one that perhaps you would remember is that once one of these ones did do that, and they crashed in and landed just off the coast of Mexico. And that was the one that caused basically the death of the dinosaurs. And if the dinosaurs hadn't been killed off by this event, we wouldn't be here today doing this lecture, because all the mammals are the ones that survived and the dinosaurs wiped out. Now, maybe the dinosaurs would have evolved to be highly intelligent, but probably not, because their brain and so on was quite small and was never going to sort of develop like we have, like mammals have. So we do sometimes think that these things are quite useful. We would not be here. Now, there are other parts of the solar system. If we go right at the far end, there is something called the Kuiper Belt. And this is where all the kind of rubbish left over from the formation of the solar system exists. Again, in the courses here we do at Kent, we talk a lot about stars and planet formation. And we also do a lot of research in this area. And when a sort of star system forms, any planetary system forms, you've got quite a lot of bits of material. They collate together to make the planets, but some of the stuff is left over. It's got to go somewhere. And in our case, it sits out there at the edge of the solar system, and what we call the Kuiper Belt. And Pluto is just at the edge of that Kuiper Belt. It's one of the closest ones in, and it's a Kuiper Belt object. So maybe it's not a planet. It's a bit of this stuff. It's also out there where the comets come from. They're out there and they come in, and we'll look at that later in this talk. And particularly those comets come from the Oort cloud, and it's a long way away, but these periodic comets, they sit out there and they visit us every so often. We don't always know when they're going to come. There are one or two, like Halley's Comet, which are able to be predicted. They come in, they go around the sun, they go back out again. But often we get comets just popping up here, there, and everywhere when we look for those. And Kent likes comets. And there was a particular mission called the Rosetta mission, which some of you might have heard about. And this was the first mission where we sent a spacecraft to a comet. And we not only went to that comet, we actually landed on it. And I was very lucky to be involved in that mission and actually working with a team that built one of the instruments that actually landed on the comet. And other colleagues here at Kent were very much involved in looking at the chemicals and the elements and the structure of that comet. And that was great fun. Okay, so that's the kind of rough guide. And now what we're going to do is go through a little tour, planet by planet, and try and tell you something about what we know about each of the planets, where we're going to them, some of the exciting missions that are going to come up, and some of the things that if you were studying a degree at Kent, you would learn more about in the courses. You might end up doing project work on them, and you might graduate and end up doing PhDs working on one of these planets or one of the moons of one of these planets, etc. So I'm going to start with the inner planets. And the first one is the one closest to the sun, and that is Mercury. Now, it happens to actually be the smallest planet in our solar system. It's about 0.4 of the diameter of the Earth. As I say, it's closest to the sun, and it goes around the sun pretty fast. The Mercury year isn't 365 days, it's only 88 days. Now, the interesting thing about Mercury is that it doesn't really rotate. So one side of Mercury is always looking at the sun, and the other side is looking away away from the sun. So one side gets very, very hot, and the other side remains very, very cold. So you've got a huge temperature difference across the surface of this planet, from minus 173 centigrade to plus 427 centigrade. So although it's very close to the sun, it actually does have ice caps. It does have ice because it's not rotating. So as I say, some parts of it are always in the kind of shadow and never get warmed up. So it does actually have ice on it, even though you might think it couldn't possibly have ice in it because it was so close to the sun. But it doesn't have any atmosphere. It doesn't have any sort of nice little clouds or anything around it. It really is just a rocky planet with some ice and on it. Now, there are two space missions currently going to it. One is called Messenger, which was the American mission. And what you will hear constantly in this talk is usually there are two missions. One, an American-led mission, and one, a European, usually in collaboration with somebody else, either the Chinese, or the Russians, or the Japanese, who we are working with. But you'll always find that there's usually two missions. And Mercury had the American mission that usually gets there first, And Bepi Colombo is the European mission, which is on its way there now. So just a few facts again about Mercury. It's dense. It's actually quite dense. You know, its density is about 5.4 grams per cubic centimeter, which means that it's quite heavy rock. But the surface is quite light. There's that sort of powdery stuff on the surface. And we kind of think that looks a bit like the same stuff that we're seeing on the moon. The core is made up of iron and nickel, and that core is about the size of the moon. Why is it so large? Because, as I say, most of the other material has been blasted off and accreted away, so you're left with the heavy stuff. It hasn't really done much for about the last 3.7 billion years, which is about the same age as we have here on Earth. For earliest formation of life, we think it's about 3.2 billion years. So Mercury's kind of been sitting there doing not a lot over the most of the history of our solar system. Now, as I say, the Americans got there first. They've taken some really nice pictures of the mission to Mercury. It ran from 2011 to 2015, and many of the pictures that we've got of Mercury's surface come from that mission. And here you can see some of the photographs taken by the messenger going around the planet, and you can see here some of the craters and so on its surface. Now, as I say, we're really excited because the European mission is on its way, and it will arrive there on the 5th of December in 2025. And that is a joint mission between Europe with the British and the Japanese. And so we will be being able to investigate a lot more about Mercury's surface. We'll be able to look at the ices on it and look about the history of this very interesting planet. Now, the next mission, we've come back out now. So what's the next one? Well, the next one is Venus, and Venus is often called Earth's twin. It's nearly the same size as the Earth, 95% of the Earth, so it really is pretty close. It rotates around its axis quite slowly, so it takes a long time to rotate around, so Venus days are quite long. And it spins backwards. So unlike us, it goes the wrong way round. The surface temperature is horrible. It's 377 to 487 centigrade. So you really don't want to be on the surface there. You know that water boils at 100 centigrade, so you won't find much water on there. However, it does have clouds, and these clouds have been seen, but they're not water clouds because obviously that wouldn't we haven't got much water there. So the atmosphere is mostly carbon dioxide. Now, if you were standing on the surface of Venus, the pressure there is 100 times higher than Earth. So you would feel pretty squashed. So what's happened, and you say this is one of the planets that you can see in the night sky without a telescope. So you could go out, I think tonight, it's a bit cloudy here where I am, but most nights you might be able to go out and actually see this planet up there. You certainly just need binoculars. You don't need a telescope to see it. And what we think's happened on Venus is it was a bit like the Earth, but it kind of had a runaway greenhouse effect. It had global warming gone mad. And so the CO2 built up and built up and built up and formed such a temperature inversion, such a big temperature, that essentially the surface became completely dry and bleached. The surface does change, however. It's not that old. It's probably 300 to 500 million years old. We've got some craters on it. We've got some effects there which tend to suggest that, again, it's got a bit of a core. And it hasn't got a magnetic field. So it isn't like the Earth. We've got a nice magnetic field, which we need for our protection from the solar wind. But we've got some nice pictures of it. And here are some pictures of what we think the surface looks like. You can see on the right there, you can see that we've got some clouds. We've got some clouds. We might have some lightning. Now, if you've been listening to the news in the last few weeks, you will have heard about Venus. Venus has been in the news because people found a chemical in its atmosphere called phosphine. Now, phosphine on Earth, the only way that we know we can make this compound is by life, by biological organisms ejecting it. And so there was a huge surprise when people on Venus found this molecule. And so there's a lot of debate in the papers. You can go onto Google, you can go onto the internet, and you'll see lots of debate about it, where there's a belief that, well, how could that get there? How could there be phosphine? And so people are talking about the idea that if there could be life on Venus, maybe it's a form of bacterial type life that can exist in clouds. We know that bacteria exist on clouds on Earth, so they could exist on clouds on other planets. So this is really one of the really exciting things why Venus is in the news a lot at the moment. But like all good science, there's an awful lot of debate about it. And again, if you do a science degree, you'll be able to learn about, for example, how you weigh up evidence. And if you read on the internet, you'll see the thing there where people say, well, yes, they've got this signal, but is it definitive? Could it be due to something else? Could it be what we call a false positive or whatever? If, on the other hand, it's confirmed, it might be the reason for spending a spacecraft to go and look a bit more. But you have to choose these missions. You only get probably 1 or 2 space missions a decade. If you're a scientist, you probably only get to work on maybe 3 or 4 in your career. And they cost a lot of money. They cost hundreds of millions, if not £1 billion pounds or euros to go. So you have to be pretty sure that the science you want to do is there. So that's why there's a lot of debate at the moment about Venus and whether there could be life in its clouds. It does have volcanoes, though, and these clouds are actually mainly sulfuric acid clouds. So this is another reason why people are worried about, oh, well, how could life survive in those? And as I say, the pressure at the surface is very hard. So we got some pictures. This is one of the few pictures we've got of an instrument that managed to get through the atmosphere of Venus. It went through the clouds, and basically it got eaten by the sulfuric acid. So it could send the data for a short period of time, and then it just melted, basically. But we have got some pictures, and we do know that the surface is covered in sort of volcanic floodplains where the lava was flowing across the surface. And at the moment, I think it's about 1,100 have been counted, something like that. About 1,100 volcanoes are possibly across the surface of Venus. And so the surface looks very much like these plains. And this is just one of them. This is a famous picture that was taken. This is called Mat Mons. It's about 8 kilometers or 5 miles high on the Venusian surface. It's not the biggest volcano in the solar system. We're going to see that in a moment in the next planet, but it gives you an idea of the sort of thing that we can look for. And you can see these rather nice, interesting structures, these pancake domes that are seen. Again, these are related to the spreading of the material across the surface. So we don't exactly know how they're formed and exactly the details. We've got nothing quite like them on Earth. So we've got to sort of think a bit more about them. All right. So Mercury, Venus, now we come to our own planet. So I'm not going to say too much about the Earth, but just to remember some of the things about the Earth and how it compares to other planets. So first of all, it's quite, as a planet, it's a reasonable size, 7,900 miles, nearly 13,000 kilometers in diameter. It's not quite a perfect sphere. It's a spheroid. It has a tilt, and that's very important. It's tilted at 23 degrees. And if it wasn't tilted, we would not have our seasons. We would not have summer and winter. We would have the kind of the same climate all the year round. So the degree of tilt is another aspect when you look at planets. You want to see whether they're tilted on their axis. The temperatures go from -73 in the coldest parts of Antarctica to about 48, 50 degrees centigrade in the hottest places are Death Valley in America and also in Ethiopia, where we are doing experiments on the Rift Valley. But again, sometimes it's dangerous going to these places. We actually just have to pull all our people out of Ethiopia because, again, if you've been looking at the news, there's some fighting going on there and there's some war. And in fact, the university we were collaborating with just got bombed the other week. So sometimes going in the field as planetary scientists can be a bit dangerous even on Earth. Now, the Earth has a very thick atmosphere. It's got to have an atmosphere. It's got to have some chemicals in it like CO2 to act as a kind of heating blanket. Again, what we call the greenhouse effect. That keeps the temperature up, so it's nice for us. But of course, we put too much of this material in, it will get hotter and hotter and hotter, and we don't want that. But the other thing about the Earth, it's got lots of water. It's got lots of water on the surface. 4/5 of the Earth, we've got lots of water, and that calls us a water world. And we don't have many other water worlds. It's one of the ones that we look for in other solar systems, in other planets around other stars, because if we could find something that looks like a water world, they're the good candidates for life. Now, just again, remember that the Earth, it's very geologically active. We have our own volcanoes. It's got tectonic plates, which is also believed to be very important for life. It's got a magnetic field because it's got this iron core in the middle, and this rotation of this iron core sets up the magnetic field. And if you do not have a magnetic field, you have a problem, because all these nasty particles coming from the sun hit our surface. It wouldn't make our lives very nice. In fact, we probably wouldn't be able to live on the Earth's surface. We'd have to live underground. And how do we know about this solar wind, as we call it, interacting with the Earth's surface? Well, we get these rather nice effects called aurora. Now, I don't know if you're watching this webinar, how many of you have actually seen them? They are dramatic. I mean, if you ever get a chance to see them, do. Getting to Antarctica is a bit difficult, but in the Northern Hemisphere, Iceland's a very good place to go. Iceland's a great place. If you ever want to do geology or planetary science or anything, Iceland is the country you really want to go to, because it's got everything. It's got volcanoes, it's got glaciers that look like icy plains on other planets, and it's got aurora, it's got everything. But you can also go to Norway. And if you're up in the top of Scotland, you actually get them a few times a year, the aurora. If you have a big storm, you get them. And that's just due to the solar wind hitting the Earth's surface, producing loads of electrons that cascade down into the atmosphere and produce these beautiful colors, as you can see here. And the lower picture is really nice because it shows that you see, for good reasons about the way of the Earth's magnetic field, you see these aurora as a kind of like a crown on the Earth. Around us there, and you can see here, this is one here, you can just spot, maybe some of you can spot Greenland, the biggest one there. You can just see Iceland just below the halo here, and then you can see Europe with all the stray lighting down there. But again, Iceland's great because it's so empty that again you don't get all the effects of light pollution. You can just go out into the countryside outside Reykjavik every evening. You could just drive out for 30 minutes and you can just sit there and watch these marvelous displays. And if you've never done it, it's one of the kind of bucket list things. Do it once in your life. Okay, so now let's move to our nearest neighbor on the other side, if you like. Venus on one side, our other nearest neighbor on the other side is Mars. And again, you can see this in the night sky without a telescope. You can get the binoculars, you can look at this, you'll see it as the red planet. It's about half the size of the Earth. It also has a tilt, which means it also has seasons. Pretty similar to the Earth. It has seasons, it has summers, it has winters. It rotates about every 24 hours. So again, very similar to Earth. The Martian day is called a sol. It's very, very similar. But the year is a little bit longer. It takes 687 days rather than 365 days to go around the sun. But it's very different to Earth. It's very cold on Mars. It's between about -83 and -33 centigrade. So even your Martian summer is not the best place to go outside. It does have an atmosphere, a very thin atmosphere, made up again mainly of carbon dioxide and just a tiny bit of nitrogen. And there is no water on its surface like Earth. We do have ice. It does have polar caps, North Pole and South Pole. It has they are made of CO2 ice and water ice. It also has two little moons called Phobos and Deimos, which are probably captured asteroids. They mean fear and terror. And they are the first asteroids that we think we might go to and actually mine, because asteroids are believed to have lots of nice minerals which we might need, like, for example, some of the rare metals we need for electric car batteries or for your mobile phone. And we're running out of them on Earth, or we have to mine them in places we really shouldn't be spoiling. So some people think the best thing to do is to go to asteroids and get these. The advantage of Phobos and Deimos is that we know where they are and they stay there. They're not like other asteroids moving through. We can actually know where they are, go there, land on them, and maybe bring some of these minerals back. As I said, the gravity is about 38%. So it's a lot less gravity than on Earth, which means that's one of the reasons why the atmosphere has disappeared. There wasn't enough gravity to hold on to it. It does have a thick crust, and in the past it supported volcanoes. It used to have a magnetic field, but it doesn't seem to have one much now. Bits of Mars occasionally get knocked off and come to us as meteorites. And we've got about 38 meteorites on the Earth, which we believe have come from Mars. And all of them are about 180 odd million years old. So we've got these. As I said, it does have volcanoes, or it does still have volcanoes, but they're not active. And the biggest one is called Olympus Mons. Currently, it's the largest one in the solar system, and you can see roughly the size of it here. It's roughly the size of France. You can see here I just superimposed the volcano on top of it, but it's dormant. It hasn't gone off for millions of years. But in the early stages of Martian life, it was there. It led to the fact that there was an atmosphere, and the temperature therefore was higher, and therefore potentially there was water on the surface, and there was potentially life. Now we have rovers that have gone around Mars. There are some up there now. Again, you can go onto the internet and you can type in the various Martian rovers and see what pictures they've been taking today and where they are. They have a lot of sand dunes, and there's some very pretty things about sand dunes. And again, I'm lucky enough to work with people in Denmark who actually mimic these sand dunes. They kind of build them in the lab, and they look at Martian sand dunes and how they move with the winds and everything else. So we can get an idea of why these patterns occur on Mars. We can replicate them ourselves. But this is what they kind of look like. If you take a picture, there's a famous Viking image up there. It gives you an idea of what the surface looks like. On the right is a picture of the ice cap. We do quite a lot of interesting things with ice caps. We can study how they change as a function of the seasons, as they expand and they contract. And that's quite a nice piece of interesting science. But as people started to take more and more accurate images, and we've got images of Mars's surface pretty much similar to Google Earth images, that kind of resolution, we can really look in quite some detail. And what we do when we look is we find structures that look like water was flowing. We know what water does. It flows down hills and it produces like sort of little streams and so on, and that leaves a trace in the soil and so on. And we've seen the same. But this surface hasn't changed for millions and millions of years. So it happened in the past, but clearly at some stage on Mars, there was water. And so we need to think about that. And if it was there for a long time, and this is a sort of artist's impression of what Mars might have looked like about the same time as life was emerging on Earth, then it looked pretty similar to us. Well, if life was emerging on Earth, why didn't it could have emerged on Mars at the same time? All the conditions were pretty similar. The difference was that Mars then, because it was so small and it didn't have a big, the magnetic field wasn't so strong, and the atmosphere sort of evaporated, then gradually it dried up. But we still are very, very interested about going to Mars, looking for signs of old life, might be fossilized life, and looking for things below it. And again, this brings us into our next mission. This is called the ESA mission, called ExoMars. Now, ESA, European Space Agency, has already got instruments flying around the surface of Mars, taking photographs and so on. But we're all very excited because in 2022, the European rover, partly built in the UK, will be going to Mars, will be landing on Mars, and it will be doing its own work around. The previous missions have predominantly aimed to look at the geology. We want to look for life. And the other really interesting thing which is going to be trialed is we're going to try and fly a little helicopter, a little drone, if you like, on Mars. And this will be the first time that any human instrument has actually flown. And you can obviously see the advantage if we could actually get a drone to go onto Mars, because then rather than wait, these rovers move very slowly, a few tens of centimeters per day, per week. But if we could take a drone, we could cover a much, much larger area of the surface much more quickly. So that's really exciting thing, an exciting piece of technology that's being developed. But remember, the atmosphere is so weak, all the things about trying to make a drone fly, like trying to fly a kite, it's quite difficult to get your kite to fly sometimes. Well, the problem is we've got to try and do this on a planet which we've got to be trying to send radio signals backwards and forwards to it. And that takes a period of time. So it's a very, very difficult piece of technology, but very exciting if it works. Okay, so we've taken our journey. We've gone around all the inner planets. They're exciting and they're great. But what about going out now into the second part of our solar system, where now we're moving away from rocky planets, so no longer Earth-like planets, going into things that really look very different. They're just basically huge balls of gas. And these are called the gas giants. Now, they are much bigger normally. Here's a scale diagram of the big four. Jupiter is the biggest planet by a long way, but Saturn's pretty big. And Uranus and Neptune are also quite large compared to the Earth. So they're all big. They're made up of mainly gases, hydrogen, particularly. They've sometimes got other things like helium and methane. Somewhere underneath all that gas, there is some possibly small core, small little bit of rocky core. There's something in there, but we don't know much about it. And we don't know much about its surface because we've never been there. And okay. So the big one is Jupiter. It's huge. It's 11 times the size of the Earth. It's twice the mass of all the other planets combined. It's 318 times the mass of the Earth. And it's got a big pressure. So I'm sorry, this is an American number, but I couldn't translate it into kilograms. But if you're weighing 100, you've got 100 pounds on the Earth, that would weigh 254 pounds on Jupiter. The atmosphere is mainly made up of methane, water, and ammonia. And as I say, there's some kind of rock underneath, but we don't know what it is. We think it's a kind of metallic hydrogen because it generates an electric field. There must be something down there that is metallic, that is rotating, because Jupiter has a big magnetic field and it has what we call a big magnetosphere, and it throws out a lot of particles into the planets around it. Because it's so big, you can go and see it in the night sky again. You don't need a telescope. In fact, you can easily see it with your naked eye. It's got clouds. If you get your binoculars out and you look through and you can see it, or you get a very small telescope, it's very easy to see Jupiter and see its clouds. And it rotates at about 10 hours. It's a 12-year orbit compared to Earth. And we've had lots of things that have gone to it. The first missions were the Voyager missions. We've had lots more. And now we have two missions which are very exciting. One is called Juno, which is there now. That's the American one. Remember, they're always doing it with the Americans. They normally get there first. But we are about to launch our next one. It's called JUICE, and it will launch in 2022, and it should get there in 2029. And again, academics working at Kent are involved in that mission. And some of the PhD students who are doing their PhD now are collecting data which will be used to interpret and understand the data that we take when we get there. And particularly, we're interested in the moons of Jupiter. So we know Jupiter's a big planet, but it's got a lot of moons. In fact, it's got 79 moons. We found 79 so far. We'll probably find some more, but we're about 79 of them. Now, many of them are small, but there are some big ones. And I'll come back to those in a moment. As I said, the main thing you see if you look at Jupiter are the climate. You've got the clouds and you've got weather systems, and there are some big climate systems there, like, for example, the giant red spot, which is some kind of storm that's been on Jupiter. But it's been there as long as we can ever remember, because the very first telescopes, Galileo, this giant red spot was seen then. So it's a storm that lasted 300 years. And the storm cloud, remember your pictures that you see on the TV at night, watching the storms coming across the Atlantic. Well, these storms are so big that the size of them is 3 times the size of the Earth. And the winds are a bit more than we encounter here. They're 400 kilometers per hour. So this is a big storm. Jupiter has a magnetic field, so it has aurora. And these are the first aurora that we found outside the Earth. And you can see a picture of them here. This is the auroral circle above the Jovian North Pole. They're not actually often seen in the visible. They're actually seen in the ultraviolet part of the spectrum, but it doesn't matter. That's just to do with the molecules and the atoms that you're playing with. But as I said, what we really like also is Jupiter. It's got lots of moons, and that's where the JUICE mission and the Juno mission is going to be looking at in the next few years. One of the interesting moons is this one called Io. It looks like this. It's very yellow because it's basically got lots of sulfur on it. And the reason it's got lots of sulfur on it, is because it's a volcanic moon. It's so close to Jupiter that basically the gravitational pull of Jupiter basically pulls the inside of the moon out. So it's very, very active. It's got lots of volcanoes on it, throwing out lots of material, normally sulfur material out. And we are going there with the Juno mission, hopefully, if it's approved, in the next 2 years. We'll be going to get some real close-up pictures of looking at this, and everybody's quite excited by that. The other moon is Europa. Europa has a icy surface. It looks like it's ice-covered ocean. And it's got these kind of geysers or things on its surface. And we believe that this is one of the best places to look for life in the solar system, because what we think is it's got a nice ocean underneath this ice, which is at the right temperature. It's probably got some heat coming up from the center of the moon. And so people believe that this is possibly one of our best places to go and look for life. The other moon is Ganymede. This is actually the largest moon in the solar system. It's actually bigger than Mercury, the planet. It's again got parts of it that are very old, but it's got an ocean underneath the rocks again. So again, some people think that it may have this kind of salty ocean underneath its ices. And again, another possibility of where life could have evolved in the same way as the type of life that we find at the bottom of the oceans of the Earth. You may have heard about these things called black smokers and so on. Some people believe that's where life on Earth really began, bottom of the oceans. So possibly Ganymede or Europa will have the same. And then there's another moon, Callisto, which is large like Ganymede. It's mainly made of ice and rock. And this is one we want because we also think there might be some salty oceans under there. So they've got all these moons where, forget about life on the planet, we think life may evolve on the moons. And Jupiter has got lots of interesting moons, these really big moons, Europa, Ganymede, and possibly Callisto. And that's what JUICE is going to go and find. JUICE is the mission that's going to go there. It's going to spend time going around all these planets. And every so often, particularly on Europa, some of the material in the ocean gets pushed out in like a sort of little volcanic eruption. It's called like a geyser. Again, something you can see in Iceland. And that material gets flown up. And wouldn't it be great if we could fly into the plumes of one of these things and collect it and see if there was life being thrown out into space, or maybe just the chemicals to tell us that life had been there. That's what we're hoping to be able to do in the next 10, 15 years. So carrying on our mission, we've now got to Saturn. Now Saturn is 9 times the size of the Earth. It's of course the famous one because it's got all the rings. The planet itself is made of hydrogen and helium. Again, we think it may have some kind of rocky core. It's got lots of atmosphere, so it's got lots of winds, it's got lots of climate. The winds may be, again, 500 meters per second. But it's cold. But these rings are the thing that most people get excited about. Again, they can be seen by the naked eye. They can be seen obviously very clearly if you've got a telescope and so on. It's got lots of moons as well. It's got 82 at the moment. It rotates quite fast, 11 hours, and it takes about 29 years to go around the sun. Now, this planet is one that we've been looking at for the last 20 years. Because there's a very, very famous space mission called the Cassini-Huygens mission. This was actually the very first mission for people in Europe to build spacecraft and take them out there. Everything else had previously only been built by the Russians or the Americans, so NASA or the Russians. But Cassini had a probe called Huygens, which was built in Europe, and in fact, part of it was built here in Kent in the Department of Physical, what's now the Department of Physical Sciences. So as I say, you can see it the naked eye. These rings are what we're fascinated about. We know a lot more now about these rings. We know a lot more about the number of these rings. We know about the temperature of these rings. They're all made of little icy particles, slightly different types of ice, different chemistry of the ice, different structure of the ice, lots of different things about it. And we now know a lot more about it because we've been able to fly up to them. We've actually been able to fly through them, which was very exciting. So we've got some real information about what these moons are made of, these rings are made of. But it has the moons, and it has one particular moon which we are really excited about, and that's called Titan. And Titan is believed to be the moon that looks closest to what we think the Earth looked like at its birth, when we were just starting to form life on Earth. And we believe that by studying Titan, we can study our own atmosphere, our own birth on here. It's a bit cold. Its average surface temperature is a minus 179 centigrade. It's got an atmosphere not of oxygen or anything like that. It's made up mainly of methane and argon, mostly methane with a little bit of nitrogen. Mostly nitrogen with a bit of methane. But it's important because it's got the carbon. It's got the molecules which we need for life. We are a carbon-based life species. The atmosphere is quite thick. In fact, if you look at the planet, all you can see is the atmosphere, this orange ball, if you like. And on the surface, the pressure is higher. Now, we have an interest in Titan, as I said, because it is possibly British. Because when Cassini-Huygens make there, this is the picture of the Huygens probe. So Cassini was the space craft, and the probe that was sent into the Titan's atmosphere was called Huygens. And it parachuted down through the atmosphere, and on board it, it had lots and lots of instruments. At the bottom of the instrument was something called a penetrometer, which measures how hard the surface is. So basically, when you hit the surface, what the penetrometer does is it sends up a signal, a kind of shock wave. And if it's a hard surface, you will get one type of signal. If it's a squishy surface, you'll get another signal. If it's a liquid, you'll get another signal. That penetrometer, as we called it, was built here in Kent. And it was built by John Zanecki, and the team at the time was in the what is now the Department of Physical Sciences, then the Department of Physics. So the very, very first thing to land on Titan was not only British, but it was from Kent. And I like to think that in the old days, when you went around the world and people went and discovered, in inverted commas, because often they didn't really discover it, because often there are people living there, but when people went from Europe around, when they wanted to claim somewhere, they would stick their flag in the soil and say it's now part of the Spanish, British, French, Dutch Empire. So that interesting thought that the very first thing ever to land on Titan was British. So maybe we should claim it for Britain, or even for Kent. When that instrument landed, it started to take some photographs. And these are some of the photographs it took. And it was taking photos as well. This is like a river system. This is the only planet where we can see that there is actually liquid material flowing across the surface. But it's not water. It's methane, it's ethane, and it's hydrocarbons. But it has got a river system. And it's the only thing so far in our solar system that we know that has a river system. And it shows very similar geological effects of a river system. It just happens not to be water. It happens to be hydrocarbons. And this is a sort of picture taken from when the Huygens probe, when you can see sort of, you'll see something here. In fact, what we did, and what one of the PhD students spent their time doing, was actually trying to work out what the signal from the penetrometer was. And first, people thought that maybe it had landed on something which is kind of like a hard surface with a bit of mushy stuff underneath. So it kind of called it creme brulee. But now we think actually what had happened was it landed on a rock. It landed on a stone. And so it landed on the stone and skidded off it. That's what we think actually happened to the Huygens probe. And then this was the picture it took. And you can see some of those boulders, which maybe it bounced off when it landed. Now, Saturn has some other moons as well. Mimas and Phoebe look really interesting because you can see they really look like being mashed up. They've obviously been in some kind of collision. They've got huge craters which have almost split them in two. So at some stage, it was a bad time out there. Things were being really pummeled by other things. This is my moon. This is one of the moons that I work on. This is called Dione. It's a picture taken from Cassini. It's an ice-covered moon. You know, guess by now I like ice-covered moons. And we've been looking at this one for the last 5 or 10 years, trying to work out the chemistry of this and trying to understand the science of Dione. So if you come to Kent and do a degree and you get me lecturing you, you'll hear about Dione, and you'll also hear about my other favorite moon, Rhea. which is a bit smoother, but still got a lot of interesting stuff. The other interesting moon of Saturn is this one, Enceladus, because if you look at this, you're going to start to see some similarities with those moons of Jupiter. You can see some stripes in this one. So this is one where we believe that underneath that ice surface, we may have an ocean. And so we've got an ocean again, possibly. It's warm enough, it's liquid water, so it must be warm enough to sustain liquid water. So maybe it's warm enough to sustain life. And this is believed to be kind of similar to what you might have as those nice oceans underneath the Antarctic ice sheet as well. So we can compare this with the lakes that we know exist underneath Antarctica. And we know that there's water down there because every so often the surface breaks open and a geyser throws out some surface jets of the water from Enceladus. And here's a picture taken, lovely one. You can see these jets, these 3 jets coming out, where this ocean material is being thrown out into space. Sadly, Cassini missions didn't know we were going to find these, so we could never actually fly through them and collect any of the material. We could only just look at them. We didn't know they existed until we got there, but wouldn't it be wonderful to go back and have a look at what's coming out from the inside of this moon? And there's some other moons, Avitus as well as an interesting one as well. Okay, so I've got 2 more to go, 2 more big planets, and then we talk about what might be a planet. And that's the next one is Uranus. Now, Uranus is the first planet that you can't see with your naked eye. So this is the first one that you have to get a telescope out to look at. And so therefore it was the first planet was discovered using a telescope, and it was discovered by William Herschel here in Britain in 1781. So that's some time ago. It's a bluey looking planet. It's a gas giant planet. It's about 4 times the size of the Earth. It's blue because it's got a lot of methane in it, and the atmosphere, it's got hydrogen and helium, but the methane in it basically makes it look blue. We've only had really 1 mission to Uranus, and that was the Voyager flyby. So actually, we don't know very much about it. We've got a few pictures of it. We've got a bit of spectroscopy of the atmosphere, but actually, we don't know much about it. And the other moon, the other planet, Neptune, also looks blue. So it's also kind of something that's got these methane and these hydrocarbons in it. And we've again only had 1 flyby of that. It's got a big spot on it. It's got a big storm on it, a bit like Jupiter. But this is the dark spot. This is a blue spot rather than a red spot, or white spot, if you like. And we don't know how long that lasts. It might not be there anymore. Some of these ones may have died out. We don't know because we haven't been there for a while. It's currently got 13 moons, but we probably are a lot more. If we actually got there, we'd probably find a lot more of them. But as I say, we really haven't been there. We've only really been there with Voyager in 1980s, 1989. So this is one that if you're thinking about a career in planetary science and you're thinking about planets to go to in your lifetime, I would suggest Uranus and Neptune are good ones because we've got to go there sometime. But Neptune does have a big moon. It has a very big moon called Triton, and it's one that has volcanoes, but these volcanoes are not throwing out lava. They're like geysers. They're throwing out icy material. And it has some huge ice mountains and ice cliffs on it, which are melting and moving. And again, we saw them with Voyager. We've got some beautiful pictures of what they might look like, but we've not been there since. So we really don't know how it's changed. And this might change a lot as it goes around the sun and gets closer and further away from the sun. So we really don't know much about it. And it would be, again, a fascinating place to go back to. So those are what we now say is our planets. But now we come to our little friend called Pluto. Because after people had found Uranus and Neptune, they kept looking and they found this little planet, as they called it then, called Pluto. Now, Pluto is interesting because here's a picture of Pluto, an old picture of Pluto, and you can see next to it there's another system, and that's called Charon. It has a moon. It's a bit like the Earth. It has a big moon going around it. So the Earth has got a moon around it. Pluto's got a moon around it. It's got 2 little smaller ones, Nix and Hydra, which are small, maybe captured asteroids again. It's much, much smaller. It's smaller than our own moon. It's 2/3 the size of the Earth. It goes around the sun in about 248 years, so you can imagine it's a very long year. It rotates about every 6 days. Sometimes it even goes inside Neptune's orbit. So sometimes it's out beyond Neptune, sometimes it's inside Neptune. It's so far away that sunlight takes 5.5 hours to reach it. Its surface is water and methane ice. And when it gets close to the sun, it heats up and it produces an atmosphere. And we've been there recently. In the last few years, an American mission called New Horizons actually got there and took some pictures of it. And you can see the left here, you can see that it's got this red topping on it, which is due to the hydrocarbons, which we know on the surface and so on. So people are still debating, is it a planet? And you have to ask is, when is a planet a planet? What makes a planet a planet? So we have some definitions. It has to be orbiting a star. It has to be round. It can't be a star or a moon. It has to have kind of got rid of material around it, enough gravity to sort of make itself clean up material around it so it isn't surrounded by gunk. And so that's why people say that Pluto's done all of that. So yes, it's possibly been a planet. But other people say, no, it isn't a planet. It's small. It's elliptical. It's same material as all these other things out there, the Kuiper Belt objects. And we found other things out there which we don't call planets that are now bigger. And some of the ones on the bottom left there, you see some other things that we found. We don't call them planets. We call them either trans-Neptunian objects, i.e. beyond Neptune, or we call them Kuiper Belt objects. Quasar, Orca, Sedna, Eris, these are all mini planets that we found out there that look like Pluto. So if we call Pluto a planet, we've got to call all of these planets. So we don't want to do that. So we've given them a name and we call them planetes. We call them kind of mini planets or dwarf planets as a kind of compromise. But at the moment, Pluto is the only one that kind of has a big moon next to it as well, Sharon. You can see the two. So it's a binary system, as we call it. So what's beyond Pluto? Well, as I said, those objects are beyond Pluto, the ones I've just talked about. They're all in the Kuiper Belt. So we've got a lot more Plutos beyond Pluto. And New Horizons mission is going there now. But some people think that out there somewhere, there is actually another planet, bigger than Pluto, the sort of size of maybe Venus or Earth. And sometimes this is now called Planet 9 or Planet 10. If Pluto's not a planet, we'll call it Planet 9, if we call it Planet 10. And the reason we think it's there is because of gravitational effects. People have done models, and they think the only way to explain how some of these objects in our solar system are there is because there has to be something bigger out there that's keeping them there from gravity. So some people are still hunting for that Planet 9. But maybe it's not easy because it's not in the plane we look at. It's tilted. It might be above and below our plane of vision. So people are still hunting for Planet 9 or Planet 10. And beyond that, out there somewhere are where all these comets come from. And again, if you read the news and you've been in the news recently, you know that we think some object came into our solar system from out there. And it's a comet that maybe came from another solar system or beyond. So we have a mission now, and again, Kent are involved in it, called Comet Interceptor, where we hope to launch a spacecraft into space, make it sit there outside our one, and then when we see one of these objects, send it off there to go and rendezvous with it and see what it is. And we're hoping to get that approved and funded and off in the next 10 years. Well, that's our solar system. But now we know that our star is a rather boring star. And around those stars, all those other stars out there, there are lots of planets. And we call those exoplanets. And we now know that there are thousands of exoplanets, which we've seen around stars. And we're only seeing a tiny fraction of them because the resolution we can measure is only tiny. So out there, really out there, there are thousands of stars with thousands of planets, some of which may be habitable. And maybe on some of those stars, life has evolved. And so maybe one day it will be time to boldly go and go out there with instrumentation and see whether we can find evidence for life out there. And that, of course, is where we started in the 1960s, when people started to think about the space missions and they started the Star Trek series. Well, when they wrote that Star Trek series in the beginning, nobody knew about planets around other stars. We'd never seen one. Now we know they're very common. But that's another lecture. And if you want to learn about that, come to Kent, take the space science course and learn about planets and learn about exoplanets. I hope you've enjoyed this quick guide to the solar system. I will take some questions, but I'm going to hand back, I think, to Emma.
Okay. Hi, everybody. I'm Emma. I am in my 4th and final year of the Astronomy, Space Science and Astrophysics MPhys course. And I'm basically here to answer any of your questions that you have about physics at Kent.
I will also take any questions if anybody has a burning question about space. Yeah. I'm going to stop sharing the screen now.
Okay. Yeah, we've got the Q&A thing that we can bring up.
Yeah.
If anyone has any questions. Yeah, that was a nice refresher from my lectures with Professor Lowry about all the different planets. Indeed.
So Emma, as nobody's answering any questions, you can maybe just tell people, why did you choose to study planetary as sort of ASA degree, and what made you choose that as a degree, and what made you choose Kent?
So that was like space was like what I was really, really passionate about, and that was what I knew that I wanted to specify and get into the astro side of physics way more than the physicsy physics. And so I really liked that the course was very, very specialized, and it was a lot more specialized than any of the other courses that I'd seen. And so I really liked that. And for me, Kent was like far enough away from my parents that they weren't here all the time, but close enough that I could go home if I wanted to. And so that was very nice.
Where's that? Where were you celebrating Christmas? Because I can see you got the Christmas lights up.
Yeah, I'm in Essex at the moment, so not too far away. Okay. But yeah. And I also just I had a really good vibe going around the campus, and everyone was really friendly, and the lecturers were really nice and seemed to know what they were talking about. And so that was very good.
Great. We've got a couple of questions I've noticed in the Q&A in the chat. In the chat, somebody's asked, how do I get to Mars? Well, that's a very good question. Again, in your, if we take, say you're now, I don't know, 16 to 20, and you've got a life expectancy maybe to 80, 90, I think it's fairly likely that in your lifetime, humanity will go to Mars. They're already planning for it to be a Mars astronaut and so on. A mission to Mars will take about 3 years. It will take you about a year to get there. You've then got about a year to stay there before the alignment helps you get back for everything else. It'll take a year to come back. So it will be quite a long mission. The first step, of course, is to go back to the moon, and most all the big space nations are planning to do that. I think, as Emma, we will actually have our first woman on the moon, probably within 10 years.
2024, according to NASA.
That's possible, but I don't know if you noticed, some of you may have seen on the news this morning, one of the big rockets that was being tested for blew up last night. So, there's a lot of testing that needs to go on. We don't want to have any accidents. But yeah, we will go back to the moon, and then we will start to plan to go on to Mars. So anybody who's listening and is thinking about their lifetime, I think we'll get there. There's a lot of dangers about there, being in space. The radiation in space is not a good thing. You've got to design all those things and so on. So, and you can't, if you fall ill, you can't just sort of pop back and, back to the NHS that's not going to happen. You've got to look after all that as well. So one of the things that people are also working about is what the team should look like. Who should be the experts on a crewed mission? How many should there be? What's the optimum number of people to be in that crew? And what should the makeup be? Should it be a mixed crew? Should it be a single-sex crew? Should it be, what should the expertise? There should certainly be a doctor. There definitely has to be somebody on space medicine. So I have a colleague who did his degree about the same time as me. He is a medic. He's a practicing medic at University College Hospital. He does trauma. At the moment, he's working on COVID. But I won't call it a hobby because it's much more than a hobby. He's actually a space doctor. And he actually does work on trying to talk about the physiology of people in space and the effects of long-term things like that. That's a specialism that he does. Yeah. So that's a question. Yeah. So how do I get to Mars? become an astronaut, and you might get there.
Yeah.
Do you think there could be life trapped in the ice of planets? Well, the answer to that is I rather hope that there's life underneath the ice on those planets, and I hope it isn't trapped, because because if it's trapped, it's kind of a bad thing for life. We'd rather like it to be moving around and doing stuff. But if you're asking, can I sample the ice and find evidence for the life in the ice? That's probably very good. And that's one of the things we would like to do. We would like to look for evidence of life in these ices, maybe in those geysers I showed you coming out from some of the planets, or even in the future, landing on one of these icy moons and drilling down and picking some stuff up.
Yeah, I think we're far more likely to find life under the ice in the subsurface oceans than we are in the ice itself.
Yeah. So we just got to get there and drill for it. Okay, does the course go into nebulae? I'm extremely interested in space, but I think I found my course for after college. Most of my hobbies include space, astrophotography, and such. So, Emma, do you learn about nebulae and those sort of things?
Well, we were actually doing it last week.
Right.
We briefly covered some nebulae and molecular clouds, but it's not a topic that we have like a specific module dedicated to, but it comes up in quite a few different astro modules over the years, and so you get like a good insight over the course of the entire degree.
And there's a follow-up to that one, and I know you're going to be able to answer this one. How are stars categorized? What's different types of stars?
So they're categorized, it's like a size and temperature thing, and it's you got the letters, and it's also, so it goes O, B, A, G, wait, no, A, O, B, A, F, G, K, M. I think that's the right order.
Yep.
With O being
You've also got other
hottest
things
star.
like brown dwarfs. You've got different life cycles of stars as they go through a life cycle. And I think Dirk's probably taught you all about that, Emma, about the life cycle of stars and how stars are born and how they expand and how they die.
Yes.
And indeed, if stars didn't die and throw out all the material they do, we won't be here, because that's where we get all the carbon and the heavier elements which are necessary for us. So we had the early stars, which you see by looking back and back and back in the early stage of the universe. And then a lot of the stars are the sort of chemical factories, and we are actually just bits of stardust. Ultimately, we're just bits of, all our carbon came from dead stars. So we're just bits of dead star, really.
Yep, which is quite cool, I think.
Yeah. So here's one. This is a good one. You can think about this one, Emma. Is there any possibility perhaps some life forms discovered or undiscovered on Earth began as extraterrestrial organisms?
There's quite a lot of theories about that, because we've got meteors from other locations in the solar system, and it's almost certain that some of them brought at least some water, and so there is of course the suspicion that they may have brought some living organisms with them as well, but we haven't been able to prove it either way.
So that's called panspermia. That's the idea that you can move life between things. And as I said, we know that we can get Martian meteorites. So if you want to find meteorites, they're landing all the time. But normally you don't kind of find them terribly easily. The best place to do is to go to the Antarctic, because there you have large parts of the Antarctic where the weather doesn't really change. There's no storms or anything else. And they just sit there, and you can just walk over the ice, over the snow, and you find these little black things lying around, and they pick them up, and they're your meteorites, and you bring them back, and then you analyze them. We actually currently have a postdoc at Kent, Matthias, who went on an expedition. He's from Belgium. He went on a big expedition from Belgium. All the Belgian scientists went down there, and they had a whole summer season down in the Antarctic, and they collected loads of meteorites, and he's brought some of those back, and he's now analyzing them at Kent and with other instrumentation. And when you cut a meteorite open, you find it's full of molecules, which are kind of what we call the precursors of life. There are lots of amino acids and those sort of things, and we can analyze those as well. So that's why people think that a lot of the chemical ingredients for life possibly came from meteorites and asteroids in the early days, and we can look at that. And as I say, we also have got, I think it's 38 meteorites, which we know have come from Mars because of, again, geological composition. And we can look inside those and see what the kind of atmosphere, the little pockets of gas trapped in them, which might be what the Martian atmosphere was like at the same time as we were being formed, life here on Earth. We are still getting more questions. It's very good.
Yeah.
Okay, right. Okay, this I think is one for you, Emma. What deep sky object do you find the most interesting?
So I personally, I'm more of a solar system kind of person. But in terms of like deep sky objects, nebulae are like so
So
cool.
Aubrey here, they like the Orion Nebula because it's the
Yeah,
nearest stellar nurseries.
yeah. Like you get the pretty pictures from them, which is great, and then you've also got that they are the places where stars are forming, and so they're definitely like the most interesting places to look for things that are happening.
Okay, well, we'll see if any more questions come in. Emma, would you like to? What are your plans for the future? You say you're a year 4, so what are you contemplating now? What's the big plan?
So next year I'm hoping to do a PGCE, so that's a teaching qualification. And I'd be teaching in a secondary school, but I do want to focus on science education more generally, to do with science outreach and things like museums and observatories, providing information just to the general public.
Well, I think you're going to be very good at that. And that's very important because it's very important to have people who teach the people maybe on this some of the passion as well. And obviously, if you know your subject well and you're passionate about it, I think you teach it very well. And science communication is again something at Kent that we're expanding. We were very lucky. We've just won a big award for our science communication and trying to embed that in our degrees. So you've had some opportunities to give talks and presentations, Emma, and
yeah. So there's we've got like a mentorship scheme at the uni, which is really, really good. And also the Physics Society, they run a present your passion talk, and so you do like 5-minute presentations, and that's been really, really cool because you can just talk about whatever you want for 5 minutes and it doesn't have to be physics related as well. And obviously doing outreach like this, which has been really, really fun.
Yeah, and I think we strongly encourage all our students to go out and be ambassadors and talk about the things that they learn in physics and in space, but also in chemistry and other topics as well. And we are a department that has physics, chemistry, and forensic science, which is also useful because a lot of the questions in space aren't just physics. There is chemistry, as I've indicated tonight as well. There's geology and so on as well. And if you really want to look about the origins of life, you have to learn some biology, which is why you hear terms like astrophysics, astrochemistry, and now the new one, but very exciting one, astrobiology. So all those things, and indeed, I think, Emma, you had the astrobiology taught to you by Penny?
We had some taught to us by Penny and some taught to us by Matthias.
Yep. So you get to learn a little bit about that as well. So although you might be doing a physics and a space science degree, you do learn other things as well, because you have to if you want to look at the whole space section. Yeah. Right. I think we had one something about taking the photographs that got them into photography. I'd love to be able to implement it into a career in the future. Well, there are actually people who specialize in space photography. Even today, it's specialist skills, but think of all those pictures. So if you say you're a photographer and you really wanted to get into space photography, surely the best thing to do would be to one of the people who actually build the cameras that go on the spacecraft. And one of my former students does exactly that. He works for a company in Switzerland who design many of the space cameras. And again, yeah, his interest started off by photography. It was always a pain whenever we went on a conference because he would spend all his time taking photographs. You'd walk every 10 minutes, he'd take another photograph. But now he actually builds cameras to go on spacecraft and take those pictures I showed you tonight. I think that's really cool.
Yeah. Also, in terms of astrophotography, we have the Beacon Observatory, but also the Space Society have a telescope on campus that you can go and use and take photos with if you want.
And Emma may not know this, but as of this week, we're getting a second telescope, a robotic telescope has been given to us, and we will be installing it in January. And the great advantage of having a robotic telescope is that though I'm sure you love going to the telescope in the cold, dark winter nights when it's cold, You'll actually be able to sit at home and use the robotic telescope as well. How about that?
Excellent.
That will be on campus for students joining us next academic year. We're literally signed off the installation build today, so it will be up there in December. So you'll get a chance to have a look at it in January, February, Emma.
Excellent. Where can I find more information about the course for the future? It should be on the University of Kent website.
Yep, you can go onto our web pages, but I'm sure if you wanted to contact, if any of you want to contact us, you'll see my name on there and many of the others, and the admissions staff always happy to talk to you about options, opportunities, or just generally about, you know, what's it like to be a space scientist and what careers and so on there are.
Yeah, Dr. Kinnear is very enthusiastic.
We are indeed. Well, come on. Exploring the solar system and visiting other planets. You can't get bored with that. Come on, can you?
Yeah, that's true.
Okay, we're 10 minutes, I think, past the scheduled time. I don't want to stop people if people have got any other questions. It's great we've had so many.
Oh, we have one quick question. What do you learn about black holes? So we learn, I'm trying to think, it's second year or third year. We learn like the mechanics of black holes, how they kind of work, what they actually are, rather than what science fiction would have you believe that they are. And really as much about black holes as we can know at the moment, considering how difficult they are to observe.
Yeah, they are. I mean, obviously, again, people have probably seen that they've got the new information on black holes and so on. Yeah, that brings in some good deep physics as well, and you've got to understand some quantum mechanics. So Emma, you've learned some quantum mechanics in your time, and I think you've just come from another talk with a little bit of quantum mechanics.
Yeah, I've got my quantum mechanics textbook right
here.
here.
Look at that. That wasn't even planned. Well done. No, I mean, that's also an important part, and understanding some of the cosmology and other stuff. Yeah, you need to understand a little bit of quantum mechanics because that's how the universe works. So we do need to understand that. Okay, what is actually an astronaut in terms of education? Ooh, that is an interesting question. Most astronauts, there are two types. I mean, astronauts have to get sort of several things. One of them, they have to be incredibly fit. So you do actually, if you're going to be an astronaut, you actually have to go through quite an extensive training schedule. So you'll find a lot of astronauts were pilots in the past. They were usually something from the military, but it is changing. You know, space flight is becoming less hazardous and dangerous and more sort of compatible, but you still have to be pretty fit. But increasingly, well, if you look at the space station and so on, increasingly astronauts are doing science, and Tim Peake was doing science when he was on the space station, and he is hoping to go back. So a lot of them are trained, some of them are engineers. And let's go back to that thing about going to Mars. Think about the team you would take with you. One of them will have to be a doctor, as I said. Maybe one of them's going to be very good at electronics and communication, somebody very good at IT and computers, maybe.
A pilot.
Pilot, yep, absolutely, be able to do something like that. So it's very, astronauts will become very varied. And to be honest, going back to you, Emma, you actually do need to have somebody who can communicate as well. So somebody who's got very good communication skills and is very good at being able to put things to the media and to the public and everything else would also be very good. So don't give up on being an astronaut, Emma.
I won't. Yeah, space agencies tend to have a lot of requirements. I think that one of the most important ones is a minimum of a master's degree in a relevant field.
Yeah, you have to learn quite a lot. Yeah. But as I say, most of us won't actually will never probably be astronauts, but the team that goes behind it and all the people who work on those missions, that's just as exciting, you know. So you don't necessarily have to be the one up there. You can be the people doing the other stuff, which is all vital because it's a huge teamwork effort as well. And that's the other big thing about space and planetary science. You know, we have to work together, all nations, all cultures, everybody has to work together. And you know, a lot of the rivalries and so on, we just don't have that. We just work as one big team because at the end of the day, we're all just people on Earth trying to explore out there. And it doesn't really matter where we're from on Earth. We all want to work together to the same thing.
Yeah.
Anything else you'd like to say, Emma, about your time at Kent, or any other things that you'd like to recommend people to say or anything?
I mean, I can't sell the course enough. I've really enjoyed it. I'm very sad that it's my last year. But yeah, like I've had a really good time at Kent, and it's been really, really great.
Well, nobody, as we've been trying to build up, particularly in the last few years, the community, we are trying to build a school and a community. So once you're part of that community and once you're part of that family, you will never leave. You know, you'll be one of the things that hopefully you will look back upon with great fondness in the rest of your life. It's an important part of your life going to university. You'll make great friends and it will be that kind of period of your life. And so, yeah, hopefully if you come to Kent and you enjoy our time here, you will always be part of that family, and hopefully you will always find ways of engaging with us. No matter what job you're in, you'll be coming back and talking to the next generation of
Yeah.
students and everything else. And yeah, we would be delighted if any of the people watching tonight were here in a few years' time and said that they, by joining in this webinar tonight, it incited them to come, and they maybe, you know, they would be doing what Emma's doing in a few years' time, talking to the next generation of why they come, and they'll have just as good an experience. So Emma, thank you ever so much.
Thank you.
Can I wish you a good Christmas?
Yeah.
Take a little bit of a break because you're going to be going into exams and so on next term, I guess, a little bit.
Not next term, term after.
Wow.
No, it's dissertation next term.
Dissertation, you got it. But anyway, take a little bit of a break. Thank you ever so much for being here tonight.
Merry Christmas. Thank you for having me.
Everybody who's joined tonight. Do get in touch with us if you've got any other questions and so on. And I hope you've enjoyed a little bit about learning about the solar system, and it's inspired you to think a little bit about the opportunities of being a space scientist in the future.